we're going to talk about LeChatelier's principle. So yesterday you did, or today you did, a lab that should have kind of introduced you to the idea. And so here's our official lesson with it. If a system in equilibrium is disturbed by changing its conditions, or what we call applying a stress, the system shifts in the direction that will then reduce the stress. And if given sufficient time, a new state of equilibrium is established. Okay, so there's a few different ways that we can do this. And we'll first look at disturbing a system by changing concentration, by adding or removing reactant or product. Okay, so if we add a reactant, let's say we add in more A, then we have too much reactant, not enough product. So what's going to happen? Well, we're going to consume that reactant and form more product, and so we'll say that the reaction shifts to the right. The products are on the right. Well, what happens if we add a product? Well, same idea, but on the flip side of the coin. Now we have too much product, and so we'll use up the product, form more reactant. We say that the reaction shifts to the left. Now we could also do this by removing reactants or products. So if we remove a reactant, we take it away. Well, now there's not enough of it. So we shift the reaction to, that should say left, shift it left. And if we remove product, it should shift right. So switch those two. Sorry about that. Given the following reaction at equilibrium in a closed container at 500 degrees Celsius, predict the effect of each of the following changes on the amount of ammonia present at equilibrium. So if we force more hydrogen into the system, so we have more reactant, it's going to shift it towards the products, which is to the right. What if we remove some ammonia from the system? It will shift it right as well, because we've got to make up for that lost product. Okay, so if we're doing this in an industrial sense, removing the product, whatever it is that we desire, is actually really useful because that shifts the equilibrium continually to the right so that we get more of whatever product. Okay, yay for economics, right? Okay, now, with gases, we can do things like changing the volume and pressure. So let's say we've got this hypothetical system where we have A yielding 2D. If we decrease the volume, okay, we're in effect increasing the concentrations of everything. Well, notice that D is squared, so we're changing that much more than we are A. Okay, so we'll actually shift towards the fewer moles of gas. So here, for this scenario, it would be shifting left. If we increase the volume, the reverse is true. It would shift towards more moles of gas to shift right towards the product. You can also think about this in terms of the pressure. So if we increase the pressure on a gas, then we are decreasing the volume. So it's the same as decreasing the volume. Okay, now not every system will shift left or right with this. It's just particular to this. So here's the big idea. Okay, first off, if there's no change in the total number of moles of gas in the balance, so if we have like 3 and 3, then a volume or pressure change won't affect the position of equilibrium. But if we do have a change in the number of moles of gases, decreasing the volume or increasing the pressure will shift towards the smaller moles of gas. And increasing the volume will go towards the larger moles of gas. Okay. And just think about it in terms of the math, or think about it in terms of your little seesaw, if you will. I mean, that's what equilibrium reminds me of. It's a little seesaw and getting stuff to balance. So let's try this. Given the following reaction at equilibrium, predict the effect of increasing the pressure by decreasing the volume. So I see I have 1 plus 3, so that's 4 moles of gas versus 2. So if I decrease the volume, I'm going to go to fewer moles of gas. So here it will shift right towards the products. Okay. Well, let's try this equation. Same thing, we decrease the volume. I have 1 plus 1, so 2 versus 2 moles of gas. So here, we won't have a change because we have 2 moles of gas in the reactants and in the products. Okay, changes in temperature. Well, think about exothermic reactions, heat. You write your heat term as a product. Endothermic, you write it as a reactant. So you're then going to treat heat as a reactant or as a product. So increasing the temperature in an exothermic reaction is adding more product. So that would shift it left towards the reactants. In an endothermic reaction, though, it would shift it right because we're going to use up that reactant known as heat. Okay, now, told you at the beginning of this that there's a relationship between Kc and temperature, so now we're going to think about it. Okay? Now, this is the only thing that changes Kc. So, pressure, more reactants or products, catalysts, they don't change equilibrium. Only temperature will. And you can look at various Kc values to let you know if a reaction is endothermic or exothermic. So let's think through this. Okay. If I have my exothermic reaction, adding heat will shift the reaction left towards the products, towards the reactants. And so the more and more reactant favored you get, the more and more Kc will decrease. So for an exothermic reaction, Kc values will decrease as temperature increases. And the reverse is true for an endothermic reaction because it shifts the reaction to the right. Adding heat shifts the reaction to the right. And so your Kc value gets greater and greater as your product becomes more and more prominent. You can always look at something that way. Okay, lastly, LeChatelier's principle and a catalyst. Well, catalysts, remember, lower the activation energy, and they lower it for the reverse and the forward reaction. So they don't shift equilibrium. It will speed up both the forward and the reverse reaction. So catalysts do not change equilibrium. Like, repeat that little mantra to yourself. Catalysts do not change Kc. Catalysts do not change the position of equilibrium. And here's your 2 mastery checks. They will be on Google Forms. So what's the effect of increasing temperature on this equilibrium? And this one, which equilibrium reaction shifts to the product side when temperature is increased at constant pressure and to the reactant side when total pressure is increased at constant temperature? There you go.